This is Chapter 5, Section 3, Part 2. And starting here, we're going to discuss oxidation numbers. Now, oxidation numbers are numbers that are assigned to an atom in a polyatomic ion or in a neutral molecular compound that's based on the assumption of electrons being completely transferred. So we're essentially trying to figure out where the electrons are located within this molecular structure. In an ionic compound, there is a complete transfer of electrons, so we can tell that electrons have moved from the positive metal to the negative nonmetal. If we have a covalent structure, then the electrons are not represented by a charge, and that's where these oxidation numbers come into play. We're going to give them these oxidation numbers to represent what would happen if those electrons were transferred. So there's a couple of rules with assigning oxidation numbers. One is that the sum of the oxidation numbers for all the atoms in a compound must equal 0. And the second is that the sum of the oxidation numbers for atoms in a polyatomic ion must equal the charge on that particular ion. So if it's the ammonium ion, it needs to equal +1. If it's the phosphate ion, it needs to equal -3, whatever the charge is on that particular ion. Now, here are some rules for assigning oxidation numbers. Any free element, which means that they're uncombined with other types of elements, are automatically assigned a 0 oxidation number. So like sodium metal is just a 0. O2, well, it's not combined with any other type of element, so we're giving it a 0 oxidation number. Any monatomic ion is going to be the same as the charge on its ion, so K+, that's going to be a +1 oxidation number. If you have a binary ionic compound, then the more electronegative element, that's what En stands for, which is always going to be your anion, okay, is going to be the same as its charge if it were an ion. So here, chlorine is going to be -1, just like it would be normally. Hydrogen is generally going to be a +1. Now, sometimes hydrogen can be combined with a metal. If it's combined with a metal, and so hydrogen would be listed second in the formula, then its +1 would switch to a -1 oxidation number. Fluorine is always going to be -1, just like its normal charge, and oxygen is going to be -2. Now, there are a couple exceptions with this rule as well. Most of the time, oxygen is going to be -2. If it combines with fluorine, it'll switch to a +2. And if it's in a peroxide, it's a -1. So like H2O2 is hydrogen peroxide. Then this oxygen is going to have a -1 oxidation number. And the last one is that if in compounds, group 1, 2, and aluminum are all going to be +1, +2, and +3 respectively, just like they would be for their normal charges. Now, here's some types of problems that we're going to do. You'll either be asked to determine the oxidation numbers of a compound, in which case you will have to determine every single element in that compound, or you'll have a problem like this where it says determine K in KOH, so one single element within that compound. Now, KOH is a neutral compound. It does not have any charge written anywhere, so we have to set our problem equal to 0. Now, I usually write the individual oxidation numbers at the top and the totals at the bottom so I can see where I stand. So here, if I'm trying to find K, then that means that there must be a rule about oxygen and hydrogen. So if you look back at the oxidation rules, you can see that oxygen is a -2, so I write that above it, and hydrogen is a +1, so I write that above it. And there are only one of each of these. So total, I'm getting -2 from oxygen and +1 from hydrogen. Now, in order to get back to 0, then that means that this potassium must be a +1 oxidation number. Now, down here, this one's a little bit more complicated. We've got a few more elements. We're trying to determine chlorine in CaClO3 2. So, if we're trying to find chlorine, that means that we must have a rule about calcium and oxygen. Now, I went ahead and distributed this 2 throughout. It just is a little bit easier for me to see my math that way. So I made it CaCl2O6. The 2 gets multiplied through those parentheses. Oxygen, we know from the oxidation rules, is -2, and there are 6 of them here, so that means that total I'm getting -12. Calcium is in group 2, so it's a +2, and I only have 1, so I have +2 total for my calcium. Now this whole thing is a neutral compound, so it equals 0. So if I have negative 12 from oxygen and positive 2 from calcium, then total I need to get positive 10 from these 2 chlorines. But to find an individual chlorine, I would have to divide that by 2 since I have 2 chlorines here in this formula. So an individual chlorine would each have an oxidation number of positive 5 in this particular compound. Okay, now here's a couple of examples with polyatomic ions. So we're no longer dealing with neutral compounds. So with this one, I've got to determine nitrogen in the nitrite ion. Now the nitrite ion has a -1 charge, so that's what I'm setting my problem equal to, -1. If I'm looking for nitrogen, then that means that I know a rule about oxygen. And oxygen's rule is that it's -2. There are 3 of them total, so I will have -6 overall from all 3 of those oxygens. And that means that nitrogen then must be a positive 5 in order to get back to -1. Now down with this one, I'm still trying to find nitrogen, but it's in a different ion. It's in the ammonium ion. So this time it has a +1 charge, so that's what my problem will be equal to. And hydrogen, if you look at your rules, says that hydrogen is a +1. There are 4 of them here total, so I'm getting +4. And to get back to +1, then that means that nitrogen must be a -3 in this situation. Okay, so you can see how those elements can change oxidation numbers depending on what they're combining with. So their electrons are going to be located in different places depending on what they're combining with. Now hydrates are compounds that we're going to be using in lab. A hydrate is an ionic compound that has water molecules attached to its crystal lattice structure. So it looks like a solid, just a normal solid that you are used to seeing, but it actually has water attached to it. So the beginning portion of a hydrate name looks just like an ionic compound, like this one here is sodium carbonate. Then you're going to see this little dot, and then a number, and the H2O formula after that. And we're going to use a set of prefixes, which is in table 5-8 in your book, to tell us how many of those waters are attached. So this particular element, or compound, is sodium carbonate decahydrate, because deca is the prefix for water. Now what we're going to do in lab is we're going to heat up our hydrate and try to remove all the water from that crystal lattice structure. Now once we remove that water, we now refer to it as anhydrous, which means that it does not have water anymore. So the anhydrous version is just this part, just this sodium carbonate. Here are those prefixes that I was mentioning. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is going to be 10. Here are a couple examples of naming hydrates. So we start with BaSO4, that's barium sulfate. We have our little dot, and then 5 is going to tell us penta, and then the water is hydrate. This one here, we've got magnesium sulfate. 7 is hepta, so we have heptahydrate. And then this one down here, this is a binary ionic compound that has some water with it. So we have strontium chloride dihydrate. So I would expect you to be able to take one of these formulas and write a name from that, or do the opposite. Take the name and write the formula from that name.